Hi, in this video, we'll be going through the 2-point boundary value problems for ODEs. In this video, we are merely going through strategies and techniques that you can use in solving these 2-point boundary value problems. So what is a 2-point boundary value problem? Well, as we have learned already, when we have an equation over here, then we are given some initial condition. The initial condition, the point they start from t0 is the same. Then it will be like y t0 and y prime t0 equals to something. But for boundary computation, then we have two different points with two equations as well, so that we can solve for the two unknowns in the solution later on. So in that case, now we say that we have one function in terms where we sub in the point alpha and another function where we sub in the point beta. So an example is like the following, where we are given y double prime plus 2y equals to 0. So y0 is 1 and y pi is 0. We can solve the general solution for this. You'll get this. Then we just sub in 0 to get one equation, and we sub in pi to get another equation and solve for C1 and C2 respectively. Then we say that this is the solution to the boundary value problem. So in an initial value problem differs from a boundary value problem because for initial value problems, we have an existence and uniqueness theorem. But for a boundary value problem, we are unable to have a similar theorem. So those are some interesting things to take note of. Now we look at another example, and for this example, we can show that a homogeneous boundary value problem may have infinitely many solutions. So what is a homogeneous boundary value problem? Well, in that case, the boundary conditions will be equal to 0. So you shift all the y functions to one side, then when you sub in the point, then it equals to 0. And a boundary value problem is homogeneous if it has both the homogeneous boundary condition and the equation itself is homogeneous. So the equation itself is homogeneous means this equation over here, all the y's here, equals to 0. So some simple facts is that any homogeneous boundary value problem has either the 0 solution or infinitely many. Because you can actually check that if you have one solution, then any constant multiple will also be a solution. And AX is the only solution. So this analogy is similar to the one in linear algebra, where a matrix A times X equals to 0. Well, then 0 is obviously a solution, so you are either having only one solution or infinitely many. So a lot of these are analogous to the ones we have in linear algebra, so it's kind of easy to remember the terms, but you need to take note of what the terms actually mean for the specific context. So now we study one very particular important case of a boundary value problem, and that is known as the eigenvalue problem. So we are given the linear operator, so the differential equation plus some lambda L equals to 0. Then we are supposed to find this L, lambda. So lambda y equals to 0, then we are supposed to find all lambdas and can be an element and can be a complex root as well, such that the homogeneous boundary value problem has non-trivial solutions. Then we say this non-trivial solution of y will be the eigenfunction and the lambda is the eigenvalue. Just like when we have linear algebra where AX equals to lambda x, then lambda is an eigenvalue and the x is called the eigenvector. So from the previous example, we have this equation y double prime plus lambda y equals to 0. These are the conditions. Well, we can see that one of the eigenvalue is 1 and has a corresponding eigenfunction of sine x. So how do we solve an eigenvalue problem? Well, we've just solved the equation here first, and from this differential equation, the solution, then we just sub in to find the answer. So let's just look at the example. So we know that if you ignore the boundary condition first, you just solve this is c1y1 plus c2y2. So we need a lambda such that there is non-trivial solution, means c1 and c2 cannot be both 0 at the same time. So we solve for the characteristic equation, r will equals to this. Okay, so r equals to this. Then we have cases. So the case 1 is when your lambda is positive. If your lambda is positive, then this is complex. If this is complex, means that the general solution will look something like this. When you sub it in, first you sub 0, you are able to get rid of this. Then you here is c1 times 1 plus c2 times 0 would imply equals to 0 would imply that c1 is 0. And y, if you sub in the pi, then we know c1 is 0, so this part is removed. Then we have this. So to ensure that we have a non-trivial eigenfunction, we need the c2 to be non-zero. To c2 to be non-zero, we just need the sign to be 0. And this happens if and only if square root lambda pi equals to some constant multiple of pi. Then square root lambda equals to n, which means that lambda equals to n squared. And then we split to the next case where lambda is less than 0. If lambda is less than 0, we're able to make it into, we just let lambda be this minus mu square, and then you solve out. And you can actually show that in this case, both c1 and c2 will always be 0. So this will not, there will be no negative eigenvalues. And if lambda equals to 0, then you just need to solve for y double prime equals to 0, which gets you this general solution, which again shows, you sub in the boundary conditions, show that c1 and c2 are both 0. So the only trivial solution there is only the trivial solution in this case as well. Hence, to summarize the results, given the problem, we see that lambda must equals to n squared is the only types of eigenvalues, and the eigenfunctions corresponding to it is sine nx. And there are no other real eigenvalues. However, it may be possible that you might be thinking that it is possible to have a complex eigenvalue, but you can actually show that this particular problem cannot have any complex eigenvalue. And we'll actually discuss this later on in the video, that any class of these problems have only real eigenvalues. So that's all for this video. I hope you have enjoyed it. I hope you see how we solve for a 2-point boundary value problem. So we just solve this first, then we consider the cases for the lambdas. That's all for this video. I hope you have enjoyed it, and I'll catch you in the next one. Bye.